In the earlier lesson, we resolved the velocity vector into its two components, one along the x-axis and one along the y-axis. And also we discussed that we could apply the equation of motion independently along the x-axis and y-axis. So this is a two-step process, and this lesson is step 1. So we begin by launching a projectile with an initial velocity of v0 at an angle of theta. Let's first focus only on the x-axis. Along the x-axis, the initial velocity is vx or v0 cos theta, and we ignore the velocity along the y-axis for now. Once a projectile has lost contact with the hand, the only acceleration acting on it is the acceleration due to gravity, or g, and this is downwards. But in this step, we are interested only on what acts along the x-axis, so we will ignore this acceleration due to gravity, or g. If we follow the x component of velocity, or vx, we find that in the absence of acceleration along the x direction, the velocity remains constant throughout its flight. So the x component of velocity remains constant throughout. Mind you, this is not the total velocity, but only the x component of velocity, which does not change throughout the flight. Now it doesn't matter whether the projectile is here, or is here, or is here, or is here, or is at the landing point. This component of velocity does not change. V cos theta is the x component of the velocity, which is the component along the x-axis, and that does not change throughout the flight of the projectile. In order to visualize this better, let's slide another ball along the floor with a constant velocity of v0 cos theta, not v0, but v0 cos of theta, the component of v0 along the x-axis. We find that both balls cover the same displacement along the x-axis in the same amount of time. While the projectile is launched with a velocity of v0 at an angle of theta, the blue ball slides with a constant velocity of v cos theta horizontally. If we want to know the x displacement after a time t, we set up the displacement formula, which is x minus x0 equals the initial velocity times t plus half at squared. The initial displacement x0 is 0. The initial velocity along the x-axis is v0 cos theta, and the acceleration along the x-axis is 0. So we obtain x as v0 cos theta times t. So the displacement at any time t is simply v0 cos theta times the time t. So you can see that we have completely ignored what's happening along the y-axis in this lesson. In the next lesson, let's tackle the displacement along the y-axis. Just to recap, it doesn't matter where you are, the velocity vector along the x-axis would always be v0 times cos of theta. After a certain time t, suppose we are asked to find the x displacement, then all we do is we multiply this Vx, which is V0 times cos of theta, by the time t in order to obtain the x displacement. So with this, we complete the first step of the process. That is, we know the velocity component along the x-axis at any given time t, and that is easy because it doesn't change. It's always V0 times cos of theta. And we know the x displacement of the projectile at any time t. So in order to find the displacement, all we do is we multiply this constant velocity V0 cos theta times the time t. In the next lesson, let's address step 2, where we will follow a similar procedure along the y-axis. The component of the velocity vector along the x-axis remains constant throughout the motion of the projectile. The x displacement at any time t can be computed as a product of the x component of the velocity v0 cos theta times the time t. So by knowing the initial velocity and the launch angle of the projectile, we can easily compute the x component of velocity and the x displacement at any time t.